Welcome guys to today's class on practical physics. In this video, we want to discuss how to perform experiments on compound pendulum. Yes, we want to see how to do that without touching apparatus. Yes, in exam hall, in your practical lecture room, you will learn how to use your equipment and do the experiment. So this video will concentrate on how to do the practical, how to do the experiment without touching apparatus. Now, before we commence into the experiment fully, we want to recall ourselves what compound pendulum simply means. Compound pendulum is a pendulum or any swinging rigid body that is free to rotate about a fixed horizontal axis. Yes, the rigid body can be called a definite shaped body. So in this case, the definite shaped body we want to use is a uniform meter rule. A uniform meter rule. A uniform meter rule is a ruler that has a calibration between 0 to 100 centimeters. That is 1 meter rule. Yes. Now, in this experiment, if you are performing it in the exam hall, you have to use G-clamp, dex, and meter rule and do the experiment. Now, because you are not performing it live and direct, we want to use formula method to do that. Look at the typical formula for this experiment. Period equal to 2 pi root K square plus H square over GH. That tells you that in experiment for compound pendulum, this K means radius of gyration. Radius of gyration of a uniform meter rule from the center. Now, this K that is called the radius of gyration, G, acceleration due to gravity, this is the what? Length. The length you clamp the G clamp, or you fix your G clamp, that is from 0 to 10. It means you clamp it at 10. If it's 15, 0 to 15 at 0.15. So this is the individual length you clamp the meter rule. Now this CG is center of gravity. For a uniform meter rule, center of gravity is always at 50 cm. Okay. Now this is the total length of the meter rule. Because for meter rule, that is 100 centimeter rule. Now, from this formula for this compound pendulum, it sends a message to us that compound pendulum experiment is simply experiment that helps you to determine the value of 1, radius of gyration, the value of 2, acceleration due to gravity, and the value of 3, moment of inertia of that uniform meter rule from the center. Okay, so we can get radius of gyration, we can get acceleration due to gravity, we can get moment of inertia as well of that uniform meter rule. That is what this experiment will help us. And when we see how to get our table, plot our graph, after plotting our graph, we will now see how to confirm the answer for G, answer for K, and all have you. Now, for you to do this, because we want to use formula method, you will have to note that G, acceleration due to gravity, is always constant. It's approximately 9.8 meter per second squared. So everybody cannot get this value, and so it will have a range. The range is 9.54 to 10.02 meter per second squared. That is the range of acceleration due to gravity. That means your answer can fall between this range. And when it falls between this range, it means your experiment is okay. Yes. Now look at our table. Someone can say, let him use this H as it is in centimeter and run this table. But I would advise you, if you are performing this experiment, ensure that your units is always in SI units form. That means here should be H meter. 10 to meter means 10 over 100, 0.10, 0.15, 0.20, 0.25, 0.30. That means I've been able to convert this to meter. That is the SI unit. Now it is this a meter form that I'm to use here to make sure that my table is in SI unit form. Now, it is important for us to note that when we are looking for formula for radius of gyration, of a uniform meter rule from the center of gravity. That means we say the K is equal to L all over root 12. We have been able to know the formula for our radius of gyration, that is K, to be L over root 12. If you watch my video on rotational dynamics of rigid body, let me just give you a hint of what we did there. We will notice that moment of inertia of a uniform meter rule from the center is equal to ml square all over 12. You will see how everything was derived. Then the radius of gyration of any rigid shaped body is known to be square root of I over m, where I is the moment of inertia and m is a mass. So what is the moment of inertia here? We say square root of ml square all over 12m. This will cancel this. Square root of L square L. Square root of 12, square root of 12. That is how we got it. So feel free to watch the video on rotational dynamics of rigid body on my channel. Just type Chidos Daniel rotational dynamics of rigid body and you enjoy the video on that, so that you see how you will learn many more formulas for moment of inertia of any definite shaped body. Now we can now sort out the value of K, knowing our L to be 100 centimeter all over square root of 12. You use your calculator. 100 divided by square root of 12, you will be having 28.9 cm approximately. Now make it to be in watts, a meter. Changing this to be a meter will be approximately 0.29 meter, because we want our table to be in a uniform SI unit. Now I will come here and put 0.29 meter. That is the value of K I am to use. Okay, now we pick any value for G from this range. I can pick 9.6 meter per second square. Why? I just decide to pick it. You can pick any one you want, but why I pick this is, by the time approximations I am doing in the table will be done, at least if you increase the G, the increment will still be in this range, because I'm using a 2 decimal. I make sure that my decimal place is in uniform. Now to get the first value, I carry my K, put here, carry my H, which is 0.1, put here, carry my G, put, carry my H, put, and get the first value of T. First value of T will be equals to 2 pi root 0.29 squared plus H 0.10 squared, that is the first value, all over G 9.6 times H 0.10. That will be giving me, I'll press it in calculator, 2 shift pi, then times square root bracket 0.29 squared plus 0.10 squared divided by bracket 9.6 times 0.10. That will be giving me 1.97 approximately second. So I'll come here and put it under period 1.97. It has the unit on the top. Then I'll do same for the second one. I will now say 2 pi root K is constant 0.29 square plus 0.15 squared all over 9.6 times 0.15. So what I will be having is, I'll be having 1.71 seconds. Right, 1.71 seconds. I'll come again, clean everything, do for the third one. I will now say 0.29 square plus 0.20 because I'm in the third column, square all over 9.6 times 0.2. Let's see what it will give us. 1.60 seconds. So I'll write 1.60 seconds. So we'll get the next one by saying t equals to 2 pi root 0.29 square plus 0.25 squared all over 9.6 times 0.25. We'll put it in brackets. So this will be giving you approximately 1.55. Now we come again. We do the last one, 0.29 square plus 0.30 square all over 9.6 times 0.30. So this will be giving us 1.54 in 2 decimal places. Now it is important to note that period simply means time taken to complete one oscillation. Time taken to complete one oscillation, and it's put mathematically as T over N, where N is 20 oscillations, that is number of oscillations, 20 oscillations. And so we can get the value here by saying 1.9 equals to T all over 20. Therefore, T will be equals to 1.97 times 20. I will now say 1.97 times 20, 39.4. 39.4 seconds. Then I'll come to the next one. The next one will be 1.79 times 20 again. 1.71 times 20, 34.2. 1.6 times 20, 32.00. Then 1.55 times 20, 31.00. 1.54 times 20, 30.8. So we got all these values by saying the T we have times 20. That 20 is constant because that is 20 oscillations we perform. Now to get this value T square, we say 1.97 square, 3.88. Then 1.71 squared, 2.92. 1.6 squared, 2.56. 1.55 squared, 2.40. 1.54 squared, 2.37. We have gotten our T squared. Okay, so So next thing we'll do is we get our ht. Ht means h times t. H times t here. 0.1 times 1.97. 0.197. So 0.15 times 1.71. 0.26. This one to two decimal places will be 0.2. Then 0.2 times 1.6. 0.32. 0.25 times 1.55. 0.39. 0.30 times 2. 0.30 times 1.54. 0.46. We have succeeded to get our table of values, yes, without touching apparatus. That just means using formula method. We want to see how to do the plotting. Okay, so we'll be using a sketch of a graph sheet to do that. Yes, look at how standard graph sheet look like. Yes, so we can't paste it here and plot and you see it very well. That is why we use this graph sheet to demonstrate it. Now, for you to plot your graph, you need to note that you have to write your date of the experiment. Write the date first. Date equals to. Then write the title of the graph. A graph of HD square. The unit is meter second square against h square. That is meter square. After writing the title, it is important that you choose your Cartesian axis. Yes, label your Cartesian axis. And for you to label it, you need to check your word scale. You need to know your scale. When you know your scale, you can now know how to label it. Left for me, I would like to leave this space and leave this space so that I will see what I'm plotting well. I will label here. I will label here. Then here will be my HT square. I'll put the unit MS square. Here will be my H square, M square. Because if I start from the down here, I will not be seeing what I'm to write. So that is the reason why I decided to skip the first space and follow the second space. Okay? So in plotting your graph, you have to use logics. You have to apply some logics, like you need to make sure that what you are writing is easily seen. Then you have to choose an appropriate scale, a good scale. Choosing appropriate scale means choosing a number that when you assign them here accordingly, then what will happen is that you'll be able to locate the points you want to plot easily and you plot it very well. Now, I want to know if I'm to start from origin. Plot a graph of this against it. They didn't tell us starting from the origin. So, I may start from the origin, I may not start from the origin. Yes, because it wasn't specified. Point number one. Then what I will do, I will look at HT square. Means here is my vertical one. The vertical one is written first before the horizontal one. The lowest is 0.39 and the highest is 0.71. Okay? That means what I will do is I will ask myself, if I start from 0, for instance. Here, if I get the value I am to put here, let's check. 0, this is for vertical and this is for horizontal. That is, I'm starting vertical from 0. What I will do is I will say the highest minus the starting point. It means I am not starting with 0.39, I am starting from 0. The highest minus 0, that will be giving me 0.71 minus 0 equal to 0.71. I will now count 1, 2, 3, 4, 5, 6, 7. Remember, I start from here. 1, 2, 3, 4, 5, 6, 7. 7. That will be giving 0.10. That means if here the first point is 0, the next one will 0 plus 0.1, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. Okay? Then if we put it that way now, that is 0.1, 0.2, 0.3, 0.4, 0.5, you will now see that 0.39 will be around here. That is, totality of this place is vacant. That is a poor graph. That is a poor graph. That means we starting from origin will not make it to be what? Well balanced, because every good graph have to be balanced at least to cover 2/3 of your graph. If you locate your vertical and your horizontal, you have to cover at least 2/3 of each. That is about every good graph. Now, what we do, we have to clean everything. We have to clean everything and start and say, we have to clean everything and change our plan. The plan is that we are not to start from the origin. I may say, let my horizontal be 0.1. I want to start the horizontal part from 0.1 and the vertical part from 0.2. If I start horizontal 0.1 and vertical 0.2, and I say this is for vertical and this is for horizontal. For vertical, look at the vertical side. The highest is 0.71. I will say 0.71 minus 0.2. That is the first point I pick. Divided by how many space? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. 8. Divided by 8. Please. 0.71 minus 0.20. That will be giving me 0.51 divided by 8. That will be giving me approximately 0.10. The reason is that this is the first starting point of your y-axis, and this is the highest point. The highest minus the starting point, which is 0.2, because you are not starting with 0.0. You are not starting from the origin, you are starting from 0.2. That is for y. The second coordinate is called the starting point of your y. Now, 0.71 minus 0.2 will give you 0.51 divided by 8. Approximately is 0.10. That means 0.1 plus 0.2, here 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. You can see now, this is 0.71, so there should be 0.8 to accommodate that. Then for horizontal one, the highest for horizontal, where is h squared? The highest is 0.09. We now say 0.09 minus 0.01. We are starting the horizontal from 0.01 because the highest is 0.09. So we can start with 0.1 for horizontal because the highest is 0.09. 0.1 is greater than this, so we can start with 0.1. we'll start with 0.01. I decided to choose 0.01. The reason being that what I choose is close to the lowest. I choose 0.2 here because it's close to the what? Lowest. And when you now put other figures, it will cover at least 2/3 of the graph. That is the idea. Now I will now say 0.09 minus 0.01. That will give me an answer divided by how many? 1, 2, 3, 4, 5, 6, 7. Divided by 7. It will give me approximately 0.01. That is 0.09 minus 0.01. It will give me 0.08 divided by 7. It will give me approximately 0.01. So that means the approximated answer, which is 0.01, that is what we'll be putting here. Okay? So 0.01 plus 0.01, 0.02, 03, 04, 05, 06, 07, 08. So if I stop at 08, you will now see that it didn't accommodate 0.09. And because of that, what I will do is, since here is 0.01, I can say let me start 0.02. 0.02 for the horizontal axis, 0.02. So that here is 0.02, here will be 0.01. Now, what I will do is, I will say, okay, the highest 0.09 minus 0.02, that is what? 0.07 divided by 7, approximately 0.01 directly. So here 0.02 plus 0.01, 0.03, 0.01, 0.04, 0.05, 0.06, 0.07, 0.08, 0.09. You now see that it accommodates everything. Now we start plotting. 0.01 and 0.39. This is 0.02. That is for horizontal, the starting point. 0.02, 0.03. Now, here will be 0.01, 0.01 and 0.39. 39 will be around here. Then we call again 0.02 and 0.44. 0.02 and 0.44. That will be around here. Look at 0.02. 0.44 will be around here. Then 0.04 and 0.51. 0.04 horizontal, 0.51. That should be around here. Then 0.06 and 0.6. 0.06 and 0.6. Then 0.09 and 0.71. 0.09 and 0.71. We have located it. Next is to put our words. To put the line of best fit. Next is to put our line of best fit. Yes, we have succeeded to put our line of best fit on it. Now, please don't forget to write your scale. Scale is very important. Since you have noted your scale, each of these spaces is taken to be 2 cm. Look at the graph sheet. Each of these big boxes are called 2 cm. Okay, so we are taking it to be this now. Each of the boxes is 2 cm. 2 cm represents 0. This minus this is 0.1. This minus this is 0.1. So 0.1, meter second square. Then that is for what? On h t square axis. Then also 2 cm represents 0.01 meter square on h square axis, because this minus this is 0.01. So you are seeing points to note: your date, your title, your scale, label the axis, then choose appropriate scale. And choosing it depends on where you are starting from. If it is 0, 0, or if you are not starting from 0, if you are starting from 0, 0, it means you'll be saying the highest minus 0 all over the number of space. If you are not starting from 0, 0, the way we didn't start from 0, 0, this we start from 0.02. It means this minus 0.02 divided by 7 bosses. Or the other one, this is 0.71. 0.71 minus 0.2, which is the first part, divided by 1, 2, 3, 4, 5, 6, 7, 8, divided by 8, and you get us 0.1. Then you run your graph, plotting, and put your line of best fit. Now, the next thing to do is for you to get your slope and the intercept. From here, our intercept will be equals to intercept. Intercept means where it cuts the y-axis. Where it cuts the y-axis. It cuts the y-axis at, what is this point? 0.44. So 0.44 ms squared. That is where it cuts the y-axis. Now, that is for the intercept. Now for the slope, what you do for the slope is you put your ruler and okay, when you do that, you say change in what? ht square and change in h squared. Now, what is the highest point here? You take it to be approximated answer is what we are taking on. Here is about 0.68, whereas here is about 0. Here is so this our y2, this point is 0.68, y1, look at it, it meets at this point, that is 0.4. So when I say 0.68 minus 0.4, that will be giving you 0.28 meter second square. Then your y2, look at where it moves down. It says 0.08 minus your y1, approximately, let's take 0.012, because this is, we are using approximated answer. This is not up to middle. So we said 0.012. So when you minus this, that will be giving us 0.08 minus 0.012. That will be giving us 0.068. Okay? So we now say that slope will be equals to 0.28 all over 0.068. 0.28 divided by 0.068. That will be giving us 4.1176 approximately. So approximated to 4.1176. Now the question is, what is the unit you have to assign to the slope? Because when you write the slope without unit, you are wrong. Now your vertical axis was meter second square all over. Your horizontal axis is meter squared. Yes, meter squared. So this we cancel this, giving you, so that means second square over meter. That is your slope. That is the unit. So what you now put here is second square over meter. That will be the unit of your slope. Now the question is, what does this slope mean? Your intercept, what does it mean also? Now for your slope means inverse of what? G, acceleration due to gravity. Yes, so we have gotten the interpretation of what this our slope mean, because this is S square over m, and you know that unit of G is m over S square. Now this is S square over m, that is inverse of D. That is why we say this signifies inverse of G. Yes, that is the significance of the slope. Now what does the intercept signify? The intercept signifies that it represents 4 pi square k square all over G. And it is from this which is representing that we can now get the value of the radius of gyration of that what? Of that uniform meter rule. It is from this which is representing that we can get it. We'll see how we got this. Let's see how we arrive at that. Now, let's see how we arrive at this. We say from our formula T equals to 2 pi root h square plus k square all over gh. This is the formula for compound pendulum. Now when you carry 2 pi to bring it inside, it means multiply 2 pi by 2 pi. We will now be having that T will be equal to square root of 4 pi square, because 2 pi times 2 pi, 4 pi square, then you can now bring it inside. Bracket h square plus k square all over gh. Okay, the next thing you do, take this square root, remove it. So if you are removing square root, you have to put power of 2 to the other side. So it becomes t square equals, so this t square means I am removing square root. 4 pi square times h square plus 4 pi square times k square, 4 pi square k square all over gh. Now what you will do is carry your h, bring it to this side, leave g. So you will be having ht square equals to 4 pi square. You will be having ht square equals to 4 pi square h square all over g plus this g will be here, this g will be here, 4 pi square k square all over g. So at this point, it is only h that you took to the other side. It becomes this, leaving g to be assigned to this, to be assigned to this, because this is all over. That is, this is for this and for this. That means when you plot a graph for ht square against h square from y equals to ms plus c, when you plot graph of y against x, m will be your slope and c will be your intercept. So h square against ht square against h square, this will be your slope, then this will be your what? Intercept. So that is why we say that totality of this is what the intercept is representing. That is, the totality of this is what have this unit ms square. So it is from this that we can get the value of k, which is the radius of gyration. Get the value of g using this equivalent of slope, which is 4 pi square over g. Let's see how to do it. Okay, now this is our slope, 4 pi square. When you plot ht square against h square, slope will be 4 pi square over g is equals to, what is our slope? 4.1176 meter s square over m. Now what we do is carry this down, carry g up. That will be giving you that g will be equals to 4 pi square all over 4.1176 s square over m. Now you now see that since this s square over m is at the denominator, it will result to inverse itself to be m over s squared. Then you now check the value of 4 pi square over 4.1176. You press it with your calculator to avoid mistake. 4 shift pi squared divided by bracket 4.1176. That will be giving us 9.5877 and all. So approximately that will be giving us 9.6 meter per second square. That is our g, and we say g approximated to this. Recall that when we started the video, we said that g ranges from 9.54 to what? 10.06. Please note this. On your exam day, this is the range of value of your g. That means whatever you get should fall inside here. The farther you get your answer from here, the more they will subtract your answer. If you are getting 9.4, 9.3, 9.2, or 10.11, 10.11 points, and so on, it means you are getting your answer far from the range, and that can subtract more of your mark. So look at the range. You can see that in the starting part of the video, we use g to be 9.6. And now we have gotten our g. Then we want to get our k. Recall that we have gotten our g to be 9.6. Let's get our k, which we call radius of gyration. Now for our k, we will say 4 pi squared k squared over g is equals to my intercept 0.44. We just took 0.44. All these are answer we got from approximation and estimation. So when you use your normal standard graph and plot it, you get it. This is ms squared. Now, what is our g? We say 4 pi squared k squared all over 9.6 will be giving you 0.44 ms squared. And the unit of this is m over s squared. Therefore, k square will be equals to 0.44 times 9.6. Let's sort their units. This is m over s squared times ms squared. M over s squared times ms squared. S squared will cancel m squared. So the unit we'll be having here is m squared. M squared all over, because unit of this and unit of this will leave you with m times m squared, all over 4 pi squared. Now we press again 0.44 times 9.6 divided by bracket 4 shift pi squared. 0.44 times 9.6 divided by bracket 4 shift pi squared. That will be giving you 0.107, approximately 107 meter squared. Therefore, k will be equal to square root of, k will be equal to, k square is this, k will be equal to square root of 0.107. That will make it to be in meter. Square root of 0.107. That will be giving you 0.33 meters. So this is the final value of your k. This is for k square. This is for k. So k is equal to this. In the starting point of our video, we use k to be approximately 0.29 meters. 0.29 meters. Then we got 0.33. That is from the approximations we have done in the calculation. So we still have it to still tally that k is 0.33 meter. Our g is what? 9.6 meter per second square. And our intercept is 0.44 meter second square. And where this answer shoot to this from 0.29 to 0.33 is from the approximations we got from the graph, because we are using a sketch of a graph, not the main graph itself, because main graph itself will have small lines, so to speak. So we have gotten our k, our g, our intercept, and our slope. So see next video on practical physics. Thanks for watching the video.